few miscellaneous things that I wanted to mention regarding filters. So, if you recall, so far we have looked at basically trying to realize a second order filter using op amps, resistors and capacitors, and the motivation to use active elements has been to remove or eliminate the use of inductors. Okay. For one, inductors are big and bulky, they are lossy, they are whole bunch of things. So, the op amp and the associated circuitry basically is trying to emulate the function of an inductor, in the sense that it is accomplishing integration just like an inductor, so as far as the circuit is concerned, it does not know whether there is a real inductor or a synthetic one. This is within quotes an artificial inductor. Using an op amp and R and C are not the only ways of realizing or emulating an inductor using active elements. There is also other ways of doing it, and I will discuss one such way today. And with that, we will wind up our discussion on active filters. If you remember, we started off with our quest for realizing a filter using this is IN and this is RLC, and the low pass output basically corresponded to the inductor current I, right. And then we went about trying to realize the inductor using op amps R and C. Yet another way exists, and if we do not want to use the inductor here, right. So, let us call this voltage V, okay. And what voltage, what is that transfer function from IN to V? It is second order band pass, right. So, let us call that VBP, and what we want to do is be able to realize the same functionality without having to use the inductor. In other words, we are going to remove this guy and we are going to put in some black box and rather a red box here, okay. And what is the whatever we do, this red box must, whatever magic it does, what comment can you make about the current drawn by the red box? If the red box is trying to do the same thing that an inductor would do, what comment can we make about the current that is pulled by that magic box? No, it is low pass, but what is it in terms of VBP? It is nothing but this current better be VBP over SL, correct. So, in other words, you have to draw a current which is the integral of, which is proportional to the integral of VBP, right. The one way of doing that would be to simply put an inductor there, but the whole idea was to avoid the inductor in the first place, right. The only other inductor integrator that, since we need integration, the only other element we know that can integrate is a capacitor, and as usual, unfortunately, a capacitor, however, integrates. A capacitor integrates current and generates a voltage, whereas here what do we need? We need to integrate a voltage and generate a current. So, what do we do? Well, what do you, you can basically, our capacitor here can only integrate current, all right, but we need it to, but we need to integrate voltage. So, what do? We can convert the voltage we have into a current, correct. so that the capacitor can integrate it, and the capacitor will generate a voltage, but we need a current, so you can convert the capacitor voltage back into a current. That is the basic idea. So, we need to convert this voltage VBP into a current. So, what kind of control source would you use? We have a voltage, we want a current. So, what kind of control source would we? A voltage controlled current source is what you can use. So, for example, let us call that GM, and this current is nothing but GM times VB, correct? And if this capacitor is, if I call this C, if I call this C1 for instance, what comment can you make about the voltage here? It is nothing but GM VBP of S by SC1, right? And as we expect, the voltage across the capacitor is indeed an integral of the input voltage VB, correct? All right. But what do we need to do? We need to pull out a current. I mean, what is the, it's a voltage, I mean, what we have in red is a voltage controlled current source. So, what is the current being drawn from VBP at this point in time? No current is being drawn, right? But what current must we draw? What current must we draw? VBP over SL, right? So, what do you think we should do? Do we have a VBP by S somewhere? Where? Voltage across the capacitor has the same form, except that it is a voltage, we need a current. So, what comment can you make now? You need a voltage controlled current source. What voltage is that voltage controlled current source supposed to sense? Oh, it senses the capacitor voltage. Right, let us say this is also GM, correct, okay, and what should I do to the output of the GM? What is the difference? I mean, what am I supposed to do? Am I supposed to push current or draw current? Draw current, so this must be an inverting GM, and therefore must look like, alright. So, what is this current therefore? GM square VBP of S by SC, alright. And so, therefore, what effective inductance is this? So, this what do you call this box here is effectively a contraption that mimics the functionality of an inductor. And what is the value of inductance that it achieves? Well, we wanted VBP over SL, and what we are getting is GM square VBP by SC1. So, the inductance L is nothing but C1 over GM square, right, okay. And all that this box is doing is, I mean, the contraption in red, all that it is doing is taking the capacitor voltage and making it look like a current, and taking the input voltage and making it look like the capacitor current. So, this way it is simply interchanging the roles of voltage and current, okay, which is exactly what the difference is between a capacitor and inductor. What is the difference between a capacitor and inductor? The only difference is that, well, both of them are integrators, one integrates voltage and generates a current, the other integrates current and generates a voltage, right. And this guy here, our friend here, all that he is doing is simply interchanging the roles of voltage and current across the two ports, all right. And this has got, so this element, I mean this 2 port by itself has got a special name. So, if you call this V1 and V2 and this is I1 and I2, how can we write the Y matrix of this guy? I1, I2 is yes people, the first row, think carefully, the first row and what is the second row, right, flipping the signs of both of them will also do just as fine, correct. And so this is a special element or a special 2 port, this is called the gyrator. And the gyrator basically is interchanging the roles of voltage and current at one port. Now, if you look at the other port, basically, you know, port 1's voltage looks like port 2's current and vice versa. Okay, so within, you know, the appropriate scaling factors with the right dimensions. Okay, do you think the gyrator is reciprocal or non-reciprocal? And the sun rises in the east. So, yeah, so why is there so much hesitation? Is it reciprocal or it is not reciprocal? What is the necessity if the matrix has to be reciprocal, if the bimatrix has to be reciprocal, what should you have? Y? Yes, Vaibhav. Yeah, so Y12 must be equal to Y21, right? What do we see here? Well, apart from the negative sign, everything seems okay, but you know, what is not equal is not equal, right? Okay. It's not like your exams where you say I missed a minus sign and then you know this is the same thing. You understand? So, this is a non-reciprocal element. Does it make sense? All right. So, now let us all right. So, let us continue with our so this is our I am going to call this C1 and I am going to call this C2. This voltage is basically, yeah, you need a voltage controlled current source here. This is Vi, let us call this GM1, GM2, GM3, okay. And well, you already know that this voltage is a band pass transfer function, right. What comment can you make about this transfer function? Why? That volt, I mean the voltage there is analogous to the inductor current. So, this is VLP, all right, okay. And you know that a resistor can be realized using voltage controlled current sources. What do you think you can do How can you use a voltage controlled current source to realize a resistor? Connect the output to the input. GM4, let me call that minus, okay, and this therefore represents a second order biquad realized only using voltage controlled current sources, and these GMs are often called transconductors. And so these filters basically are what are called transconductor capacitor filters, which is yet another way of realizing a second order filter transfer function without using inductors explicitly. All right, are also called GMC filters. Okay. Now, what is the low pass transfer function? What is the omega naught? It's very easy to do if you if you go understand the correspondence between the LC network and this one. Pardon? No, that's not right. Yes, Karthi, what do you think it is? GM? What GM? There's GM1, GM2, GM3, GM4. Which GM? Square root GM2, GM3 by square root C1, C2. Why does that make sense? Remember that omega naught is 1 by square root LC, correct? And what is L? Square root of L. What is the inductance that's emulated? Yes, Darwin. C2 over GM2, GM3, very good, and the capacitance is evidently C1. So, 1 over square root LC is basically square root of GM2, GM3 over C1. Okay. What about the Q? Again, it's the easiest thing to do is to simply imagine the correspondence with the LC network. Pardon? C1, GM2, GM3 divided by GM4. Is this correct? Well, it doesn't seem dimensionally correct. Q must be dimensionless, correct? Yes. So, coming in, what is the formula? 1 by GM4 square root C1 GM2 GM3 by, right, this seems at least dimensionally consistent. Is this correct? Sanity check is what? When GM4 tends to 0, what should you expect the quality factor to become? When GM4 becomes 0, it's like having an LC network in parallel, L and C in parallel without any damping resistance, and therefore you would expect the Q to become infinite, so that makes sense. The quality factor, remember, is for a parallel RLC tank is nothing but R by square root L by C, and so R is evidently 1 by GM4, and square root of L by C is nothing but square root of C2 over GM2 GM3 divided by C1, and therefore if you go and do the math, you basically will get. So this is the quality. So we have S square over omega naught square plus S over omega naught Q plus 1. And the question now is, what is the DC gain? How would we do this? Pardon? Open hall capacitor. So let's say you apply a DC voltage. We already know that this is a band pass node. So what is the DC voltage here? What is the DC current? VI times GM1. Okay. What is the voltage at this point? At DC? What is the DC voltage there? It's a band pass node. By definition, what does it mean? That voltage is 0. Correct? So if that voltage is 0, what is the current flowing through this branch? That current is 0. This current is 0. So where is all this current flowing? What is the current flowing through the output of GM3? This current is VI times GM1. Correct? If that is VI times GM1, what must the voltage be here so that the output current is VI times GM1? So this is VI GM1 over GM3. So what is the DC gain? GM1 over GM. Does it make sense, people? And likewise, you can go and calculate the band pass transfer function. A couple of observations that I would like to draw your attention to. When we talked about the active RC biquad, what comment did we make about its input impedance? How did they? It was a resistor, correct? There was a resistor going into the virtual ground of the integrator. What is the output impedance? Pardon? Where were we sensing the output? Where was the output of the active RC biquad? At the op amp output, right? And if the output impedance is therefore 0. So it didn't matter that the input impedance was not infinite, because the output impedance was 0, and this way we could cascade biquadratic sections without loading affecting the transfer function, right? Now here, what do you think our situation is? What is the output impedance? Pardon? I mean, is it 0 or non-zero? That's all I'm looking for. It is non-zero, right? It's if you actually look at it carefully, it turns out to be a C in parallel with an LR in series, but it's not 0. What comment can we make about the input impedance, however? Input impedance is infinite. So what comment can we make about cascading these biquads? Is that feasible or it's not feasible? Yes, no? It's feasible because while it's true that the output impedance is not 0, right? The input impedance of the structure is infinite. So if you copy and paste and connect, the next section is not going to load the previous section because it's not drawing any current, and therefore the GMC biquads can be cascaded just like active RC. All right, that was that's one thing to bear in mind. The next thing, the obvious question that should arise is the following now. What is what is an obvious question that now arises? You've seen two ways of making filters. So what's the obvious question? And when would you tend to why do we study two, right? If one of them is better, then why bother studying the other, correct? Right, and it so turns out that okay. So, remember when we talked about the active RC biquad, we said that the active RC integrator, we said that the nice thing about the active RC structure is that it is insensitive to parasitics, correct? What comment can we make regarding about that now? Well, if there is a parasitic at this node, what happens to, what is the unity gain frequency of this integrator? It is Gm by C. So, it now becomes Gm over C plus Cp, all right. And the problem with Cp is that it is often not very well predictable, okay, and therefore, the unity gain frequency of the integrator can is not defined robustly, which means that the filter corner frequency and the filter shape is also not that well defined, okay. So, if the GMC has got a problem, has got this problem, then the obvious question is why bother with GMC filters at all, right? And it turns out that remember all the nice things about the op amp RC filter are predicated on the fact that we have an op amp which behaves like an ideal one, right? If the virtual ground, if this node is not really close to 0, then all the benefits of active RC, of an active RC integrator go for a toss. So that's an issue. So what we do therefore is if the frequencies are such that you can design a very, very good op amp, and how do we know how good an op amp we need? We discussed that yesterday. We have to choose the unity gain bandwidth to be substantially higher than 2 times omega naught times q, all right. So, the op amp better be really, really fast, and evidently technology the process technology with which you make the filter basically places a limit on how fast your op amp can be, right. And the fastest the best filter, the highest frequency filter you can make is the highest frequency op amp you can make divided by 2 times omega naught times q divided by another large number, right. We wanted, remember that 2 omega naught times q of the filter that you are trying to realize divided by the unity gain bandwidth of the op amp must be a number which is much smaller than 1, right. Okay. So, so traditionally op amp RC filters were within quotes for low speed applications, right. But what the meaning of speed is it changes pretty fast. So, 30 years ago, 40 years ago, you could barely make audio filters with active RC, with op amp RC techniques. Now that audio has become several hundreds of megahertz, right. If you are on an IC and the transistors are blazing fast, then you can make a blazing fast op amp, which means you can make a very high frequency filter. The GM, on the other hand, it turns out that it's a voltage controlled current source. What is the simplest voltage controlled current source you know? A single transistor in principle can act like a voltage controlled current source. So, there is no complicated feedback, nothing, none of that stuff is involved. So, this is an open loop structure. Right. So, these filters can achieve frequency responses that are much higher in bandwidth, right. But because this is open loop, the linearity of, it turns out that the linearity of the voltage to current conversion is most of the time significantly inferior to the linearity of this integrator. Okay. So, if you want a high frequency filter with and you can tolerate some nonlinearity, then this is the only choice, right. If you want to design, if you want a very highly linear filter, but the frequency of operation is somewhat low, then you make this choice, right. If you want to make a very high frequency filter and have extremely high linearity, you sign up to do a PhD, right. Okay. So, so that's the trade. I mean, that's the trade-off between both of these. Yes, Jishnu. Yeah, but an op amp needs several transconductors to make it work. Correct. A two-stage op amp, for example, has at least 2 stages of gain and all the associated parasitics, right. Whereas, at least in principle, the GM is simply a single transistor. The output parasitic capacitors of the transistor do not bother you because they could be part of the integrating capacitance, right, because those parasitics appear in parallel with C. I mean, it is not robust, but it integrates. You understand? So, there are several applications which need very high speeds, but don't need high linearity. And in those applications, the transconductance capacitance architecture is what is used. Does it make sense? Very good. So, this is all I had to say about filters, right? And one aspect of filters that we discussed was that they need to be the signals inside the filter must not be so large as to cause saturation, right. Then but what happens when the input signals are very small, and as we discussed, it turns out that all active elements and resistors basically also add noise.